Hello, my name is Lawrence. I'm a PhD student at the Institute of Sound and Vibration Research at the University of Southampton in the UK, and thank you for watching my presentation on the effects of uncertainty when designing a tuned-shunt electrodynamic metamaterial. I'll start by introducing the study and why it is important. Locally resonant elastic metamaterials consist of periodic resonant substructures which are at a scale that is much smaller than the wavelengths they interact with, and can be used to interact with elastic waves in a number of ways, including focusing, refracting sound around an object or cloaking, reflection, and what we will be focusing on, the absorption of elastic waves. Because these have a small form factor and are distributed across the structure rather than having a control force and mass concentrated in a single location like a traditional tuned vibration absorber, they are more suitable to applications where space is a premium or where a concentrated force or mass may put too much stress on a structure, such as thin, lightweight panels. Our idea is that rather than using a fixed passive metamaterial design, modelled using finite element software, repeated prototype runs, and requiring structural modifications to tune the structure to different frequencies, inertial electrodynamic actuators can be used as the locally resonant substructures instead. Inertial actuators can be very cheap, they can be approximated by a single degree of freedom mass spring damper model, and the dynamic response can be modified by connecting an impedance across the terminals, known as shunting. However, low-cost actuators require low-cost manufacturing techniques, and tolerances in the parameters of the devices are therefore affected. Literature on tuned-shunt inertial actuators assumes known parameters. For a small number of devices, it is reasonable to accurately measure the response of each one. However, for a large number of devices, this is less reasonable. Therefore, if the effect of the uncertainties can be quantified and taken into account during the design process, then perhaps a level of robustness to this can be achieved which does not require the characterization of every device used. So first, we have selected a suitable actuator for our consideration. This is the device that will be used for our study. It retails at a little under £3 each and has a resonance frequency of around 187 Hz. There is a manufacturer's datasheet which states tolerances on the various characteristics, moving mass, suspension compliance and so on, of between plus and minus 10%. Subject to the usual caveat that the values may have changed since the datasheet was produced. We will, however, characterise the magnitude and distribution of the variation ourselves for a more accurate picture. The actuator can be modelled analytically by assuming it behaves as the single degree of freedom model shown here. The actuator is represented by mass, Mr, stiffness, Kr, and damping, Br, as well as the effect of the magnet coil assembly, represented by the transduction coefficient, Bl, and a connected impedance. Other shunt impedances can be used, but we are considering a series resistor and inductor, as it doesn't require total cancellation of the coil resistance and inductance, and has been shown in recent studies to be an effective method of tuning the resonance frequency and damping of an actuator. The effect of the shunted magnet coil assembly can be considered as a mechanical stiffness and damper in series connected between the base and the mass, which is a product of the total resistance and the total inductance of the loop, shown here. We can then assess the response of the actuator by considering the impedance of the base to a displacement, ZR, which is the impedance that a structure would see if the actuator were mounted to it and can be calculated using this equation. As I already said, we were planning to characterise the actuator parameters ourselves for accuracy, and we did this with two experiments. We measured the dynamic response to base excitation, and we also measured the dynamic and electrical response to an electrical input. From these two sets of measurements, the full set of parameters can be calculated. And here we see the experimentally characterized distributions of the parameters, the mass Mr, the resonance frequency Fr, the damping ratio, the resistance, coil resistance Re, the coil inductance Le, and the transduction coefficient Bl. Notice that instead of the stiffness Kr, we present the resonance frequency Fr. This is because there was no obvious pattern to the distribution of the stiffness, and it can instead be estimated from the mass and the resonance frequency. You'll see that not all of the parameters, such as the transduction coefficient Bl, fall within the plus and minus 10% range the manufacturer specified. Most of them can also be approximated by normal distribution curves, with the exception of the DC resistance Re, which approximates an extreme value distribution. This shows that although there is a tolerance range, it is more likely that any one actuator will have parameters closer to the nominal, worth knowing when designing for robust performance. The effect of the characterized parametric uncertainty distribution shown here will later be evaluated. But first, we will look at how the shunt impedance affects the response. This plot shows the magnitude on the left and the phase on the right of ZR, the impedance of the actuator base to displacement, for different values of the total inductance L total. The open circuit response is shown with a solid line, with the peak falling at approximately 187 Hz. And then a negative total inductance causes the resonance frequency to decrease, and a positive total inductance causes the resonance frequency to increase. However, a smaller magnitude of the total inductance causes a greater shift. You'll notice that the total resistance R total has the same magnitude for the different values of L total, but is modified to share the same sign as L total. This is for stability, which will be discussed in later slides. This plot shows the resonance frequency on the left and the damping ratio on the right for different values of the total inductance. Where the line stops here and here is because the damping ratio increases to the point that the peak in the response has completely disappeared. We can see that there is a clear relationship between magnitude and the sign of the total inductance and the resulting resonance frequency, with the change in resonance frequency increasing exponentially as the total inductance tends to zero. Also, for a negative total inductance, the damping ratio decreases to a minimum before increasing dramatically as it tends towards zero. We can now look at the effect of different total resistances, R total, on the response of the actuator. Again, we see here the magnitude and phase of ZR for shunt impedances with a positive total inductance, tuning the resonance frequency up in frequency, and different total resistances. Again, these are compared to the open circuit response. We can see how the total resistance must be small for the change in tuning frequency to be seen. We can also see that as R total increases, as well as the resonance frequency decreasing, the peak becomes more damped. It's clear that both R total and L total need to be accurate in the design in order to effectively realise the desired response. A change in 0.4 ohms, as seen by these two lines, results in a significant change in the response. The final part of this section is that we need to consider the stability of the system. A negative impedance requires an input of energy in order to reverse the current flow. This means that there is potential for an unstable system, which would potentially cause not only high electrical current, but also high dynamic output. An unstable system could result in damage to the electrical or mechanical components, or make structural vibration worse, so it is important this is avoided. The stability of the system can be assessed by considering the poles of the shunted actuator's transfer function. The system will be unstable when the real part of any of the poles is positive. Simplification of the transfer function equation means that we can calculate the poles by solving for the roots of this cubic polynomial. And it can be shown that if R total and L total have different signs, i.e. one is negative while one is positive, then there is always a root with a positive real part. This will turn out to be one of the main limitations when considering robustness to uncertainties. These graphs show the maximum real part of the transfer function poles on the y-axis, sorted by the real part of the effective electromechanical impedance, this term. Each plot shows the effect of uncertainty in a different electrical parameter. In the left, the transduction coefficient BL, in the middle, the coil resistance RE, and in the right, the coil inductance LE. The solid lines represent the actuator when the resonance is tuned up in frequency with a positive total inductance and resistance, and the dashed lines when the resonance is tuned down in frequency with a negative total inductance and resistance. Instabilities are highlighted in red. For the variation in BL, the actuator tuned down in frequency becomes unstable at this point, which is simply determined by the combination of the other system parameters. The variation in the coil resistance, RE, is sufficient in these cases to change the sign of the total resistance, which causes the instabilities shown here for the actuator tuned up in frequency, and here for the actuator tuned down in frequency. For the actuator tuned down in frequency, instability also occurs when the real part of the effective mechanical impedance falls below the same value we can see in the left-hand plot for BL, here. We can see that the variation in the coil inductance isn't sufficient to cause instability. In this case, the maximum variation seen in the coil inductance was around plus or minus 0.04 millihenry, which means in order for a change in sign of L total to occur, L total would have to be around the same magnitude, which puts the tuning frequency well above 500 Hz, outside of the range we are considering. So some of the instabilities can be avoided by ensuring that the total resistance or inductance can't change sign. This would mean restricting these values by design to a magnitude greater than the range of characterized uncertainties. However, the instabilities for the actuator tuned down in frequency, which occur when the real part of the effective mechanical impedance is below this point, must also be avoided. When all the parameters in the system are subject to uncertainty, this becomes a complex problem, and the only option is to consider a wide range of potential cases to assess the robust stability. Here we see the effect of the characterized uncertainties on the dynamic frequency response. The uncertain cases are shown by dotted lines and the nominal is shown by a thick black solid line. Unstable cases are highlighted in red. Ignoring the phase information, we see here the magnitude of the impedance of the base to displacement for the actuator tuned up in frequency on the left and tuned down in frequency on the right. The shunt impedance has been limited so that the uncertainty cannot cause a change in sign of either resistance or inductance, and we can see that this has completely removed any instabilities for the actuator tuned up in frequency. The variation in the response for the tuned up actuator is quite unpronounced in most cases. This is due to the high damping of the nominal caused by the high total resistance required to avoid instabilities. In contrast, the actuator tuned down in frequency is unstable for the vast majority of uncertain cases. The variation in the response is also markedly more significant. To see how this would affect a structure, a simple scenario is shown here. This graph shows 4 modes of a cantilever beam as the mean squared tip velocity treated with a multi-resonator electrodynamic metamaterial tuned to absorb these 4 modes. The left-hand plot shows the untreated beam with this modal characteristic and the treated beam with no uncertainty in the actuators. The right-hand plot shows multiple possible uncertain cases, and it is clear that not only are the uncertain cases also unstable, but they result in a significant peak in the response just below 140 Hz. Clearly, uncertainties need to be considered for this technology to be implemented in a real structure. So to summarise, we have considered an electrodynamic metamaterial where low-cost inertial actuators are used as tunable locally resonant substructures. The tuning is achieved using a shunt impedance, and the realistic uncertainties in the actuator parameters are considered rather than requiring accurate parameterization of a large number of devices. In order to assess the effect of the realistic uncertainties on the shunted response, they are first characterized experimentally. Analyzing the effect on the response, it is clear that the primary concern is avoiding instabilities in the system, which could cause damage to the system or excessive vibration in the structure. Although we can avoid some instabilities, which would be caused by a change in sign in the total resistance or inductance, others may require more consideration to the point where multiple uncertain cases must be considered in the design, which leads us to consider whether it may be more practical to look at achieving tighter tolerances, specifically in DC resistance, which could be measured with relative ease on a large-scale operation. Perhaps this, alongside limiting the approach to only tuning the actuator up in frequency, could be a less complex approach. To then achieve control at lower frequencies, an alternative actuator model would be required with a lower open circuit resonance frequency. Thank you for listening.